Dear students, today we will learn about matrix row operations or column operations, and these operations are used in Gauss-Jordan method and indeterminate problems also. So the Gauss-Jordan method is used to solve the equation, for solve the linear equations. We already know how to solve the equations by using inversion method and determinant method or Cramer's rule. Now one more method is there, that is Gauss-Jordan method. Before Gauss-Jordan, we have to know some operations, elementary operations or transformations. So then we will know the Gauss-Jordan method for solving linear equations. So let us see. Objectives of this class or PPT is on completion of this period you would be able to know the elementary transformations. Apply the elementary transformations on matrices. Recap. In any matrix, what are the symbols used to denote the rows R1, R2, R3? Similarly, what are the symbols used to denote the columns C1, C2, C3? Elementary row and column operations are transformations. The following types of operations are called elementary row or column operations. Interchanging two rows or columns. Multiplying the elements of any row or column by a non-zero scalar. Third point, adding to or subtracting from the elements of one row or column the corresponding elements of any other row or column multiplied by a non-zero scalar. See here, 3 points mentioned. Once again I am repeating. First one, interchanging two rows or columns. Multiplying the elements of any row by a non-zero scalar. Third, adding to or subtracting from the elements of one row or column the corresponding elements of any other row or column multiplied by a non-zero scalar. When we do the problem, you can easily understand these points. Next, equivalent matrices. Two matrices A and B are said to be equivalent if one is obtained from the other by a finite number of elementary transformations. It is denoted by A is approximately equal to B. So simply we can say A equals to B. Notation for row and column operations. The following are some standard notations to carry out row or column operations. Row operations. First point. If R1 and R2 are interchanged, then we denote it as R1 interchanging R2. Read as interchanging R1 and R2. So the symbol we can say it is by implies R. Read as interchanging R1 and R2. Second point. If R1 is multiplied by a non-zero scalar, then we write R1 gives K into R1. Read as R1 changed to KR1 or K into R1. Third point. If we multiply R1 with K and add or subtract 2 or from R2, then we write R2 changes are changed to R2 plus or minus K into R1, or we can simply say R2 gives R2 plus or minus K into R1. Next, R1 gives R1 plus or minus K into R2, or R1 changed to R1 plus or minus K into R2. Column operations. If C1 and C2 are interchanged, then we denote it as C1 by implies C2, or we read as interchanging C1 and C2. If C1 is multiplied by a non-zero scalar, then we write C1 and C2 read as C1 changed to, if C1 is multiplied by a non-zero scalar, then we write C1 changed to K into C1. Read as C1 changed to K C1. C1 gives K into C1. Next, third point. If we multiply C1 with K and add or subtract to or from C2, then we write C2 gives C2 plus or minus K into C1, or C1 gives. So here C1 gives means C1 is changed to C1 plus or minus K into C2. So both are different, not here C2 gives and C1 gives, both are not same. That operation is different and this operation is different, because C2 gives means C2 is changing and C1 gives means C1 is changing. So remember that point. Examples of elementary row or column operations on a 3 by 3 matrix. First point or question, see here, using column operations reduce the matrix 2 3 minus 1 5 7 4 9 8 3 to a lower triangular matrix. See here how we reduce it. Solution is, given matrix is a equals to 2 3 minus 1 5 7 4 9 8 3. Operating C2 gives 2C2 minus 3C1, 2 into C2 minus 3 into C1, and C3 gives 2 into C3 plus C1. Examples of elementary row or column operations on a 3 by 3 matrix. See here the symbol, we can say identically equal to, or simply say equal. So that is identically equal, that is, or we can say equal. So 2 0 0 5 1 13 9 minus 11 15. See, both are same, but to visible the elements are different. That's why it is say the symbol identically equal to. So next step, operating C3 gives C3 minus 13 into C2. That is identically equal to. See here, C3 means third column is changed. How it is changed? C3 minus 13 into C2. So corresponding elements are multiplied with 13 in C2, and after that it is subtracted from C3. So after simplification we get, that is 259 0 1 minus 11, and third column is changed as a 0 0 180, which is the required form. So lower triangular matrix. Next, examples of elementary row or column operations on a 3 by 3 matrix. Second one, using row operations Reduce the matrix 3, 7 minus 5, 9, 8, 4, 5, 2, 6 to an upper triangular matrix. See the solution. First write the given matrix, then operating R2 gives R2 minus 3 into R1 and R3 gives 3 into R3 minus 5 R1. See, one point is observed in the left side. First we are suppose changing in R2 and R2 gives, again we started with R2. In the next operation also R3 gives 3 into R3. R3 again here R3 is, so what is left side is, that is what, which row is changed. Again that row is using at beginning in the right side. So see here R2 and R3 are changed. How changed? R2 minus 3R1. So after simplification, see the second and third rows changed. That is identically equals to, there is no change in first row. So first row as it is written, 3, 7 minus 5. And second row how changed? 3 into R1. That means 3 into 3, 9. 9 minus 9, 0. That's why here written 0. The second row, first column, first element. Similarly, corresponding elements are followed that operation. So we can get these minus 13 and 19. Next third row change to 0, minus 29, 43. Examples of elementary row or column operations on a 3 by 3 matrix. Operating R2 gives minus R2 and R3 gives minus R3. That is identically equals to 3, 7 minus 5, 0, 13 minus 19, 0, 29 minus 43. Operating R3 gives 13 into R3 minus 29 R2. Which is the required form. 3, 7 minus 5, 0, 13 minus 19, 0, 0 minus 8. See here, upper triangular matrix form. Next, third question. Diagonalizable the matrix using only row operations. Matrix is 2, 3, 1, 5, 7, 4, 3 minus 1, 6. See the solution. Given matrix is 2, 3, 1, 5, 7, 4, 3 minus 1, 6. Examples of elementary row or column operations on a 3 by 3 matrix. Okay. Operating R2 gives 2 into R2 minus 5 R1 and R3 gives R2 into R3 minus 3R1, then that is identically equals to 2, 3, 1. R2 changed as a 0, minus 1, 3. R3 changed as a 0, minus 11, 9. Examples of elementary row or column operations. Okay, continue. Okay. Next, operating R2 gives minus R2 and R3 gives minus R3. That is identically equals to 2, 3, 1, 0, 1 minus 3, 0, 11 minus 9. Here minus is not printed, but we have to put. Next, operating R1 gives R1 minus 3 into R2 and R3 gives R3 minus 11 into R2. See here, and symbol is using means there are operating two operations, applying or changing two rows at a time. That is R2 and R3. So R1 is no change, so written as it is. Sorry, R2 is no change. So R2 written as it is, and R1, R3 are changed. So that is identically equals to 2, 0, 10, 0, 1 minus 3, 0, 0, 42. Next, operating R1 gives 42 into R1 minus 10 R3. And R2 gives (42) into R2 plus 3R3. So that is identically equals to 8400 042 0 0042. So here 42 R1 gives 42 into R1 minus 10 into R3. So 10 is okay, 42, right? Now R3 42 into R2 gives 42 into R2. Okay, plus, right? So diagonalized matrix means in the diagonal matrix or in the principal diagonal, the element should be there, remaining should be 0. So in the R1 we can divide with 2 or multiply with 1 by 2, we get 42 also. So this is the we transformed by using row operations or column operations. So after observing this, I think you understand how to operate, how to change rows or columns. Summary. We have discussed about elementary transformations. Which one of the following is our elementary row operations? R1 interchanges R2. So answer is C. Which one of the following is our elementary row operations? So D is the answer. Next, if A and B are equivalent matrices, then so answer C. So this is the row operations how we did, and we use these operations in Gauss-Jordan method and determinant problems also. So previously we did some problems, and in next class we know how to use these operations in Gauss-Jordan method to solve the linear equations. So once again you apply these operations, and you do some problems from textbook and observe the example problems also, and if possible understand the Gauss-Jordan and try to do. And if you have any doubts in operations, you can call me or mail me or message me. I will clarify your each and every doubt. So thank you. Have a nice day.